In this example, we're going to learn how to handle two different situations that we've not demonstrated yet, and that is what to do with a cantilever segment and also what to do now with a fixed end. Here we got a 20-foot left span with EI, the middle span being 20 feet also, but it has 1.5 EI, and then this cantilever is only 10-foot overhang, but it has 3 EI. Right? It's the only load that, it resists the only load that is applied here in this particular situation, 3 kips per foot. And let's see how we can handle this. Right now, with this, we could say that we have a degree of freedom at B, a degree of freedom at C, and we have the rotation out here at the tip plus a chord rotation of that member. But if all we want are the moments everywhere and we don't care yet about the displacements, then what we want to do is ignore all that. Well, not really ignore, but create a statically equivalent effect and reduce the model down. We don't really care about the displacements, right? Because in initial design, we might have a guess about the relative ratios of these EIs, but we don't know what they are. And so we want to do something that gets us some internal force values, and we might suspect that the dominant effect will be bending. And so let's go get the moments that are related. So the statically equivalent effect here, of course, is that we'd have a shear value that would end up going directly into the support that's equal to 3 kips per foot times 10 feet, so 30 kips. And again, that will go right into the support if we are interested in the design of the foundation, we care, or if we're interested in the shear strength of this cantilever, we care, but otherwise we don't. It's not going to be impactful at all. And then, of course, the effect from a rotational standpoint is we got 3 kips per foot times 10 feet, that's 30 kips acting at 5 feet, so 5 feet times 30 kips would be 150 kip foots, and there's your statically equivalent model. Again, out of this model we're not going to get any direct results about what happens out at the end, that how much does this go down, how much does the end rotate. We get none of that information in the statically equivalent model because we've reduced it down, right, to just 2 spans. Now, the next part of this is that we do have, in effect, a pinned end or a roller end out at the right. We'd like to take advantage of that as well, so let's remember we got modified stiffness that will help us to do all that. So the I over the L of the left-hand span will be I over 20. The right-hand span is 3 halves of I over 20. Now, we could say that's equal to K, so that would be equal to 3 halves K. That'd be one way to go about it. But recognize that with modified stiffness here, that the left-hand span being fixed, we're never going to release that. That's the regular condition, so that's still going to be K, but this other one will be 3/4 of 3 halves K, and that would be 9/8 K. Right? And that sets up our relative stiffness values, or relative stiffness, or the distribution that is, in the following kind of way. One, we're never going to release the fixed end, so whatever gets over here stays there. Right? You could make your own joke about Vegas and whatever stays in Vegas as though that doesn't really happen, but it's at least a convenient idea here. And then sum up at the middle joint, K plus 9/8 of K, which would be, of course, 1 plus, or 8 over, that's 17/8, right? So 9/8, well, sorry, 1 divided by, what did I say? 17/8? Yeah. So 8 divided by 17 is going to be 0.47. I don't usually get more precise than that. The other one then has to be summed to 1, that's 0.53. And we've got this pinned end, which is, we got a couple of things going on here, and we got to be a little bit careful about how to handle. And so we're never going to release this because we're never going to fix this end. But we do have this 150 kip foot that's sitting there. So that's kind of a little goofy. And note here what our sign convention is going to say. Right? Remember, member end is positive clockwise, but we actually have the opposite. So in a sense, it's as though we have a fixed end moment out here that's negative 150. So temporarily what we have to do is we have to release this thing, and we have to add a 150 over here, shoot it across as a plus 75 with the carryover factor. We've temporarily, in a sense, kind of locked things down, moved it over to get rid of it, but now we're never going to touch it again. Now we'll use the modified approach. Let's see, we don't even have a fixed end moment anywhere else because we don't have any spans that have anything going on. And so there's nothing else to add up here. And note that, alright, this makes sense, right? That we have a static moment here. That means we have to have a static moment that develops that is in effect equal and opposite to that for equilibrium. And then we come over to here and we got then a net of 75 as the unbalanced moment. That's 35.3 that develops. And then the balance of that has to be coming over to this side. And we've equilibrated that. And then let's see, we shoot this across. Divided by 2 is 17.6 or 5 or so, or 17.7, let's call it. And that's a negative. And then we don't shoot anything over here because we've now released that joint. We've used the modified stiffness to distribute anything at that point, so there's nothing to come back across. And since we're not going to ever release the fixed end here, there's nothing more to do there. We actually get this done in one step, which is pretty cool. And so we end up with a minus 35.3 to the left side of B and a plus 35.3 to the right side of B. Right, sum all those that are above. We get a plus 150 over here, and a minus 150 would have otherwise been 0, right? But because we really have the static effect up there, it has to end up being like this. And we of course get then just the minus 17.7 because that's all that got absorbed by the fixed end. Really clever. We got that done in about 2 or 3 steps. If we had not used modified stiffness, we would have had to bounce back and forth here and shooting across to the fixed end a whole bunch of stuff. We would have eventually converged to this very same answer.